Hi everyone, welcome to another edition of Basics to R. I'm going to go over today the basics of how to conduct a RCT analysis. Um, we're going to spend some time here talking about what a randomized control trial is, the method that we use for doing RCTs. We'll talk a little bit about the basics to RCT analysis in terms of what we do and what we do not do. Then I'm going to spend some time talking about ANOVA, ANCOVA, and mixed linear models. And I'm going to try and provide you with a brief overview of what a mixed linear model is and how it runs and what you should be doing. And then we'll spend some time going over how we can run ANCOVA and mixed linear models using R. Now, I don't think that today is going to be overly intensive. We're going to go over a lot of stuff. But I'm going to try and give you a broad overview of what you can do to run these analyses. So first, what is a randomized control trial? Well, broadly, the way that a randomized control trial works is we take a group of individuals from some sample population that may be of interest to us. We're then going to run a baseline assessment for some outcome of interest that we have. And then we're going to randomize these individuals into one of two groups normally, the experimental group and the control group. The experimental group is going to receive some sort of intervention. That can be things like a drug or exercise training. And then the control group is going to not receive that intervention. And that can include different kinds of controls. It can be something like a waitlist control. It can be a do-nothing control group, usual care. Or it can be something that's more active in nature. So for instance, if it's an exercise trial, oftentimes we do some sort of stretching control or balance and tone, so balancing exercises, things like that. And then in addition to figuring out what our experimental group and our control group are, we're then going to have those individuals go through the experiment and the control for a certain length of time. That can be 3 weeks, that can be 6 weeks, 12 months, a year, or longer. And then we're going to follow up with those individuals at a certain time point. And that can be either 6 or 12 months down the road. And it can be one time or it can be multiple time points. So again, what we're going to do is we're going to randomize these individuals following a baseline assessment on some outcome of interest. And then we're going to look at them in terms of one or two or more experimental groups. And then we're going to follow up with these individuals later on down the road on our outcome of interest. And that can be done at one time point or that can be done at multiple time points. Okay, so when I talk about what randomization means, it means that something is completely and totally at random. And I really want to stress this point in particular because it's important to recognize that when we talk about how randomization works, it is completely and totally at random. So let's take a hypothetical situation here. So for instance, I have one of two groups. I have a intervention group and a control group that have been randomized, and it's roughly split between males and females. Now, seems like a pretty good outcome where it's very, very random in terms of who is in what group. And this is just 8 individuals for right now. However, there's other ways that these two groups could end up. So for instance, I could end up with a group that is in the experimental group is completely or predominantly male in makeup, and the control group is predominantly female in makeup. Or I could also have an experimental group that is predominantly female and a control group that is predominantly male. Now, these are completely and totally at random. So there's no telling how these groups could end up forming in the way that they do. So it's important to recognize that when we are looking at groups and we're trying to figure out whether or testing group differences at baseline, it's important to remember that how groups form themselves is completely and totally random at nature. And so thus, I ask, when do we need to test for baseline differences in these different versions of randomization, in version 1, version 2, or version 3? Now, the answer to this is going to be never. We never need to test for and compare baseline differences between groups. The differences between groups are going to be completely and totally at random. So I implore you to never, ever, ever, ever perform baseline testing of groups using hypothesis testing in a randomized control trial. Other studies, it makes perfect sense to do it, but in the case of a randomized control trial, we don't need to test this because any test of baseline differences is going to be based completely on random chance, and we don't need to test for baseline differences between groups. Okay, so next let's talk a little bit about what covariates we should include in the model. So first and foremost, we always need to control for baseline outcome in our model, and that's something that always needs to be done no matter what. Now, it's also something that we should be considering is whether we need to include other covariates, and that's something that's going to be based on what our model actually represents, and we'll talk about that in a minute. So why do we need to control for baseline? Well, here I'd like to give you 3 hypothetical examples in order to help make it clear why we need to control for baseline. First, let's look at this model here on the left. Let's assume that there are 2 groups that we have. Intervention is in green, control group is in blue, and we're looking at differences between groups at baseline and then comparing it to differences between groups at final. As you can see here, the intervention group performed quite better than the control group at both baseline and final, and it appears that both groups got better over time. Does that mean that the intervention actually caused an improvement? Well, it's hard to tell in this instance because both groups actually improved and the intervention group started off a little bit better than the control group. So we don't really have clear evidence in this case that the intervention actually did work in terms of improving whatever outcome of interest we're looking at. And let's just assume for right now that higher scores mean better performance. Now let's go with the second example here in just a moment. Let's say hypothetically that rather than having the intervention group being one that performs slightly better than the control group, let's assume that at baseline, let's assume the control group actually performs a lot better than the intervention group at baseline. But then at final, we see the exact opposite, that the intervention group performed a lot better than the control. Well, at first glance, we might think, okay, great, that means that the intervention seems to improve whatever outcome we're interested in. The control group just naturally declined over time. But the fact of the matter is that what this might actually represent is regression to the mean, meaning that the actual true score for somebody is somewhere in the middle between the intervention group and the control group at each time point, and that these people are just varying around whatever average score it is. So the intervention might not actually have an effect, and the control group might not have actually changed in terms of their actual performance. And so we have no way of knowing whether or not the intervention actually did lead to an improvement in terms of performance, or the control group just got worse, or whether it was just due to random chance around the average score for whatever variable we're interested in. However, this is the ideal way that we could look at the data, and as we can see on the right here, it's a lot easier to tell that the intervention group actually performed better than the control, and that's because at baseline, if we look at the scores, the baseline scores are the same between groups, and thus we can see that the intervention group did indeed improve relative to the control group at final. And so we can now actually make a determination that yes, while the intervention group and the control group both got better, we can see that the control group didn't perform as well at final in comparison to the intervention group. And thus when we control for baseline outcomes, it's going to allow us to account for individual variation in performance at baseline. And this is something that's going to help us confirm that the intervention isn't indeed due to random chance, or improvements in the intervention aren't just due to random chance based on baseline performance. So we always need to account for baseline differences. What about other covariates to include? Well, I mentioned a while ago that's going to be dependent upon the intervention and what outcome of interest we're looking at. So let's just look at a hypothetical here. Let's assume we have 200 individuals in some sort of population. We're going to look at whether an intervention can improve muscular strength. Specifically, we're going to test muscular strength at baseline, then randomize the groups into an experimental group and then a control group. The experimental group receiving exercise training and the control group receiving, let's just say, nothing. At baseline, we look and we notice that there are these differences between groups at baseline. Age, body mass index, that there's more males or females in the experimental group relative to the control group. There's differences between groups in educational attainment, cholesterol level, fat mass, reaction time, and episodic memory. Lots of differences between baseline, lots of differences between groups at baseline. Now, of course, we obviously don't care about testing this, but we do notice it. So should we covary for each of these variables given that they are significantly different between groups? And we inaccurately decided to test for differences between groups? The answer is no. We should never, ever, ever do or covary for variables based on baseline differences between groups. And this is why it's so important not to test for baseline differences, because it may be something that we don't necessarily need to covary for, because this is due, again, to random chance. More importantly, what variables might be good to covary for in our analyses? Well, I've got a couple ideas for things that we should look at, and this is based on things that we actually think are going to impact our model of interest. I think that age, body mass index, and male to female ratio, or biological sex, are probably reasonable covariates to include in our model, just because those likely have some impact on muscular strength. However, we need to remember that fewer covariates is probably preferable, because we want to go with the most parsimonious model whenever possible. And I'm just waiting for my next slide to move on. So hang on here, gang. All right, here we go. Let's talk a little bit about ANCOVA now. So, what is ANCOVA? So we'll just go over this again. As a reminder, we've gone through ANCOVA before, but let's just say that we have, for ANCOVA, we're talking about 2 time points, baseline and final. So hypothetically, for an ANCOVA model, I would randomize people into one of 2 groups, and then I would look at the experimental group and relative to the control group, wherein I'm looking at final minus baseline. And so here there's just the follow-up time point of final and baseline, and we're just looking at differences between groups at final after accounting for baseline differences. And so this is what our model looks like in terms of our final assessment. We're looking at whether the final assessment outcome of interest, whatever that may be, is different between groups after we account for baseline assessment outcome and our covariates of interest. So for our hypothetical model looking at muscle strength, we'd be looking at whether muscle strength at final is different between groups after accounting for muscle strength at baseline and our covariates of interest. And that's what we're going to be looking at and what we're really curious about. So how do we test missing data in ANCOVA? Well, this is something that's going to be really, really critical for ANCOVA in particular, because ANCOVA is prone to having issues with missing data. Hypothetically, let's just look at this hypothetical RCT wherein we have 2 groups, wherein we have a baseline assessment, and then at follow-up we notice that there are people missing in the experimental group and in the control group. This is pretty normal, where people are not going to finish up an RCT in particular, and we lose people to follow-up. But the problem with ANCOVA is that ANCOVA does a list-wise deletion of individuals who do not complete the follow-up assessment. So it is impossible to run an intention to treat analysis with ANCOVA oftentimes if there are missing data included. And that's why it's going to be important for us in an ANCOVA model to make sure that we impute for missing data. Now, there's several different types of imputation that we can do within an ANCOVA model. One would be something like a multiple imputation. A multiple imputation is a little bit beyond the scope of what we're going to be talking about here today, but you can run that in R as well. And that, however, multiple imputations can be something that's going to be dependent upon data being missing at random, missing completely at random, or missing not at random. And I'm not going to go into the details of this specifically, but it's important to note that a multiple imputation is really going to be dependent upon what type of data are missing and how they are missing. We could also impute data using more simplified measures, such as a baseline carry forward or a last observation carry forward, which we'll go over in our practical assessment in R a little bit later. But the important thing to remember here is that we need to impute data that are missing in order to adhere to the intention to treat principle. Otherwise, we're just running a complete case analysis. So Always remember that in ANCOVA, it's going to be very critical that you impute data if there are indeed missing data. You need to check to see if there are missing data at your follow-up assessments in order to make sure that you are adhering to the intention to treat principle. And once my next slide shows up, we'll keep going. So just hang in there. All right. So what's a way that we can account for the issue of having missing data at follow-up time points? Well, one easy way to do this, well, easy in a practical sense, is using repeated measures and then running a mixed linear model. The benefit of doing this is that it helps us to account for missing data at follow-up time points as long as we have all data at baseline. So what is a mixed linear model? Broadly, the way that it works is, again, we run the same sort of RCT analysis where we take people at baseline, we randomize them to two different groups usually, and then we follow-up assessment. We do perform one follow-up assessment, but then we perform multiple follow-up assessments. We can perform a second follow-up assessment or a third or a fourth. The important thing is that we have multiple follow-up assessments within a mixed linear model. Now, the reason that this helps to account for some of the issues of missing data is because, let's just say hypothetically, again, randomized individuals to two groups at baseline, and we see that there's people that are missing at follow-up time points. The benefit of a mixed linear model is that we're able to account for some of these issues of missing data using something called maximum likelihood estimation, which allows us to include all individuals in the model as long as they have baseline data in order to look at group differences across different time points. So again, it's really, really beneficial to do mixed linear modeling within an RCT because it allows us to still adhere to the intention to treat principle by including all individuals as long as they have baseline data, because we can then use maximum likelihood estimation in order to look at group differences across multiple time points. But however, in order to do this, we need to have at least two different time points in terms of follow-up assessments. So how does this work exactly? Broadly, we're just going to go over the basics of the math here. I'm not going to go into super detail, but I'd like to just make sure that we all have an understanding about how mixed linear modeling works. So with that said, we're going to talk a little bit about what we are looking at. So broadly, what we're seeing here is that there are two different levels for mixed linear modeling. There's a lower level and a higher level to this. Now, you can have more than two levels for mixed linear modeling, but we're just going to focus on two. So the first level is going to be the participant itself, and these are going to be data that are going to be based on the individuals themselves rather than on any higher level that's going to have multiple time points. The second one's going to be time. And so what we can do is when we look at the actual model itself, we combine those two models into a single model itself, including both the participant level and then also the time level. And this is just based on the null model, which is only including the intercept only, meaning that we're only looking without regard to changes over time. Okay, now what does this actually look like in practice? Well, in terms of what we're seeing here, if you look on the left, if there's 40 individuals, then we're seeing that there are 40 participants across multiple time points. Sorry about that. But we can see that there are 40 individuals, and then we have three different time points. So we have Y1 through Y40. Those are 40 people at time point 1, 40 people at time point 2, and then 40 people at time point 3. So again, we're including people across multiple time points in terms of our development of our model. And that's what we are doing, is we're developing this multi-level model when it comes to mixed linear modeling. And that's the important thing to remember, is that we're including this across time. So what does this look like at a little bit higher level? So we can now add a second little bit of detail, and now we're going to add predictors at level 2. So again, we're including baseline participants, but now we're going to add a predictor at time point 2 across different time points. So for instance, that can be group. And now what we're looking at is we are looking at the means as the outcome of interest. So we're looking at the mean differences of, or the means of the groups across different time points. And then when we combine that, that's what the model is going to look at. So it's a little bit extra complexity, but overall what we're doing is we're just adding a little bit more detail in terms of adding individual predictors to our model of interest. And as we can see here, then we like obviously there's a little bit more complexity, but we are still looking at participants and across time. Now, let's add a little bit more detail into this in particular. And I don't want you to worry about the random intercept point for right now, but we are including predictors at both levels now. We're going to include a predictor at the participant level and now at the time level. So again, we have multiple levels that are occurring here with predictors at both the participant level and the time level. So it's just adding complexity to the model over time. Now you might be scratching your head at this point being like, I have no idea what this actually means. So let's just actually go through what this looks like in practice, because it's a little bit different for a mixed linear model when we talk about it within the context of an RCT. So I'm going to simplify this, and we're not going to use math anymore at this point, which I'm sure some of you are probably thankful for. Broadly, this is what we are doing within a mixed linear model for an RCT. We are looking at the group by time effect at time of t plus the baseline outcome of interest plus baseline covariates, with baseline outcome of interest and baseline covariates being what we are adjusting for in the model. Time would be equal to t in this case, and time is only representative of time points after baseline, so whatever follow-up time points of interest. So for instance, time at 2, we're going to be looking at time at follow-up 1 would be what I would qualify that as. Time of 3 would be at our second follow-up assessment, and so on and so forth. And again, we can see here that we are still adjusting for baseline outcome and also our baseline covariates as well within this model. So what would this actually look like in terms of the hypothetical example that we've been using thus far? And I'd like to just briefly go over that. So in this hypothetical example looking at muscular strength, we would see that we are looking at muscular strength at time point t, so whatever follow-up assessments we have is equal to group by the time at t plus the muscle strength at baseline plus covariates. And again, we're looking at separate regressions, or excuse me, separate equations for each time point of interest that we're trying to predict here. And the important thing to note with this is that, again, we are looking at things over time, because this is what we are interested in. We're looking at the individual effects at individual time points. Now, you've probably seen the term random effects and fixed effects. Thus far, you've probably seen the random effects aspect within some of the slides I've shown you previously. So let's actually describe what those are. Again, a mixed linear model is using a combination of both fixed effects or random effects, and that's why it's called a mixed model. It's a mixed linear model because it combines fixed and random effects. A fixed effect is basically an explanatory variable which has a fixed or constant relationship with the response variable across all observations, meaning that we are assuming in the case of a randomized control trial that a fixed effect doesn't vary across time. The relationship of the fixed effect variable is constant across time points, that it doesn't change across time. So within the context of this hypothetical example looking at muscle strength, the fixed effects are going to be group, muscle strength at baseline, age, sex, and BMI. Each of these we are assuming have a constant relationship with muscle strength at each follow-up assessment. The relationship between muscle strength and group, muscle strength at baseline, age, sex, and BMI do not change across time. We're assuming that those are constant. Now, time is actually a special case. Normally, we are assuming that time is a fixed categorical variable within an RCT. That's the easiest way to be able to look at that, and we're going to talk more about why we treat time as a fixed categorical variable, but it's important to note that it can also be assumed to be a continuous variable as well, or it can also be a random effect. A random effect is something that we are assuming has a different relationship with the outcome, and it varies randomly across individuals and groups. So what does that mean? It means that we can't measure a random effect. So a random effect is something that is sort of in the ether. We don't really know how it impacts a variable, and so when we talk about random effects, we actually don't measure it with a specific variable in particular, where we oftentimes are just looking at a random effect and assuming that it is different across different groups or different people. And so to do this and to be able to measure random effects, we include these random effects as something like a 1 divided by ID. This would be a random intercept, wherein we're assuming that the starting point for where an individual's slope may be in a model is going to be different per individual. So we're assuming that each person has a different starting point in terms of their relationship with muscular strength, that they have different muscular strength at the first time point within our model of interest. So again, a random effect is something that we are not actually measuring, and a fixed effect is something that we are measuring, and we're assuming has a constant relationship across all observations. Okay, let's talk a little bit more about random effects. There's several different types of random effects. There are, most commonly, the two random effects that we are most interested in are going to be the random intercepts and the random slopes. Random intercepts refers to something that is allowed to vary, and the scores on the dependent variable for each individual observation are predicted by the intercept that varies across groups, meaning that each individual has their own intercept that they contribute to the model. So the way that we do this is, again, with that one given ID term. And that's going to provide us with that random intercept, meaning each individual is going to provide their own intercept for this model. Whereas a random slope is something where the model is allowed to vary across time for each individual. When using random slopes, though, we oftentimes also include random intercepts too, in order to allow people to have their own starting point, but also to have their own changes over time. This is what the random slopes model looks like. And again, I'd point you to that time by time point t given ID, wherein we're looking at changes across time for each individual and whether they change across time for an individual. Importantly, for an RCT, we most commonly use random intercepts only. We don't typically use random slopes as well, and we'll talk a little bit more about why that is in our practical. Okay, so how does this actually work in terms of what this looks like? Because you may be thinking, I have no idea what that means. Well, a random intercept is what you can see here on the left. Each person in each individual slope line represents a single person in terms of their data. Each individual contributes their own intercept and starting point, but they all have the exact same slope. Whereas a random slopes model assumes that everybody has the same starting point, but then their slope is different. And a random intercepts and slopes model assumes everybody has their own starting point or their own intercept, and everybody's slope or change across different time points is going to be different. That each individual is going to contribute their own intercept and their own slope to the model. And it's important to note that while the slopes may be different or the slopes may be the same for individuals, we are taking the mean in terms of the slope in the random intercepts model, the random slopes model, and the random intercepts and slopes model. We're taking the mean, intercept, and slope in terms of developing the model that we're looking for. Okay, so is time a fixed or a random effect? Again, time is typically treated as a fixed effect within most of our RCT analyses. And the reason that we do that is pretty straightforward. Let's assume in this instance that I have an RCT wherein I have 3 follow-up time points. I have time point 1, time point 2, and time point 3. I've accounted for baseline in each of these. If I treat time as a fixed and categorical variable, then I can look at differences between groups at each of these time points. I can look at the differences between groups at time point 1, I can look at the differences between groups at time point 2, and I can look at the differences between time points at time point 3. This assumes that time is fixed, that this is a fixed moment in time that is not changing. However, if I assume that time is continuous and time is not a fixed variable, then what I'm actually doing in this instance, as you can see on the right, is I'm measuring the change between groups in terms of the slope itself, which is a lot more complex of a concept in terms of an RCT, because we want to see what the differences are between groups at follow-up time points. We're not necessarily interested in trying to understand what the slope of change in the model is. We want to just be able to say, yes, the intervention had an effect at this time point following the intervention. So typically what you're going to want to do is you're going to want to treat time as a fixed and categorical variable. All right, so let's put this all together. Typically within an RCT, there are 3 effects that we're really looking at in detail. The first one being the group effect. The group effect indicates the mean outcome score for each group independent of time, meaning that we're looking at independent of the different time points, what are the differences between groups? So it's the average score across all time points for each group. The second effect that we're interested in is the time effect. The time effect is interested in looking at the mean outcome score at each time point independent of group. So in this, we're just looking at changes across time, regardless of group. So it's the average change irrespective of what group somebody is in. However, the most important effect that we're looking at within a RCT is the group by time effect. The group by time effect indicates the mean outcome score for each group at each time point. And this is the most important thing that we're looking for in an RCT, because we want to be able to tell whether there are between group differences in an intervention. So let's go ahead and let's put this all together. So once we have the estimate for the group by time effects, we can then estimate our between group differences at each time point. So that is, did the intervention have better performance at each follow-up time point relative to the control after controlling for baseline differences in our covariates? So hypothetically, this is our model. We're looking at a certain outcome, group by time being our primary thing of interest, and then we're controlling for baseline. At follow-up 1, what we would test is we're testing whether there are differences between groups, with the null hypothesis being that there are no differences between groups, and the alternative hypothesis being that there are indeed differences between groups. We can then perform the same sort of assessment at other time points as well. We would test the same thing at time point 2, and then even at time point 3. So at follow-up 2, we would look at whether there are differences between groups, null hypothesis being that there isn't, and then the alternative hypothesis being that there is. Same thing being true again at time point 3. Null hypothesis being that there's no differences between groups, and the alternative hypothesis being that there is. And a significant p-value in any of these instances would represent that there is a significant difference between groups, and that, at least in terms of what we're looking at here, that hypothetically that the intervention group performs better than the control group at one or more of these time points. And that's what we're really looking for in terms of an RCT. All right, so what does this all mean? So to summarize, we would never, ever test for baseline differences in an RCT. And if there's one thing I want you to remember for today, do not ever test for baseline differences in an RCT. It's completely and totally meaningless. Do not do this. It is really bad practice. Secondly, the most common type of analysis that we can do for an RCT is an ANCOVA or a mixed linear model. While ANCOVA is definitely easier to analyze, it's a little bit harder to adhere to the intention to treat principle. But mixed linear modeling is a little bit harder to perform, as you can probably tell already, but it makes it a heck of a lot easier to adhere to the intention to treat principle, and it also provides us with greater statistical power because of the repeated measures that it has. Okay, so what we're going to do next is we're going to go through the practical here, and I'm going to spend some time with you going through how we would do each of these analyses. So first, let's go ahead and let's set up our copy of R and RStudio, and we'll get started here in just a moment. So what I'm going to do first here is I'm going to go ahead and I'm going to load some packages, and I'm going to also load our data set that we've been using throughout this course again. So if you need to, just go ahead and pause the screen. But we're going to load the ReadXL, PLYR, LME4, CAR, Broom, ggplot2, Psych, HMISC, Table 1, and LSMeans packages in order to do this. So again, just pause the screen if you need to load all these individual packages. I do also have these in the practice guide as well if you need to load, or in the sample code if you want to look through what that is. Next, we're just going to go ahead and we're going to set our working directory and load the data just like we've been doing before. I'm labeling these data 1 for right now. All right. And once we've loaded those data, let's just go ahead and I'm just going to make some changes to some of the variable names just for simplicity and ease. Go ahead and pause the screen, or you can take the sample code from that I have online and just use this. But what I want you to notice is that the way these data are set up is we have 3 time points. We have a couple different variables of interest. I have height, weight, BMI, ADAS-Cog, which is a cognitive measure, meters walked, which is how long somebody walks. Higher scores on ADAS-Cog represent poor performance. Meters walked, the longer somebody can walk for 6 minutes, would represent higher performance, being better. And then we also have education on a score of 1 to 3, and sex 0, 1, which I'm going to change in just a moment here with some sample or with some other code to make it a little bit easier to use. So what we're going to do is I'm just going to go ahead and throw some things in to change this to a categorical variable of males and females for sex, and then I'm also going to change the education variable to 1, 2, 3 for high school, trade school, and university as well. So go ahead and do that as well, just so we're all working off of the same data. But now you can see that I've got a categorical variable for sex and education as well. Okay. Now, as you probably noticed, there are 3 time points for our data in particular, and I have 120 individuals with 3 time points. Now, I would like you to note that there are missing data within those time points, and I'll show you those in just a moment here. But as you can see, we have those 3 different time points. And yes, I do have most of the data already included for everybody, but there are people with missing data, as you can see with the NA shown for several individuals for ADAS-Cog and meters walked. What I would really strongly advise for everyone, if you haven't figured this out by now, is make sure that if you have a longitudinal data set, meaning that you have multiple time points, make sure that when you are developing that data set, you have individual IDs for that for each person in your data set at each time point, regardless of whether or not they complete the study. You want to make sure that you include everyone at multiple time points. It's going to make your life a heck of a lot easier when you're developing and managing your data set for an RCT. So it's important to make sure that we include all of our participants in our analysis. Okay, so. For right now, we know that there are going to be missing data at follow-up time points for some of our variables of interest. And I can show you those on the right for right now. But just make sure, again, I would strongly advise you, in this case, you can see I have 120 observations. That's 40 individuals times 3. I would recommend that you do something similar to make sure that everyone's being included, whoever at multiple time points, or at least having a row for those individuals, regardless of whether or not they have data at follow-up assessments. Okay, so what we're going to do next is we're going to go ahead and we're going to set up our data so that way we can first perform an analysis of covariance. What I need to do is I need to change this from a long format into a wide format. the first thing I'm going to do is I'm going to take the data that are time varying, and as you can see here, I'm going and I'm taking these data and I'm looking for the variables that are indeed time varying, those being ADAS, COG, and meters walked, since I know that those change over time. And those are my outcome variables of interest for this randomized controlled trial. Whatever the intervention was, I'm looking at the differences between groups for meters walked and ADAS, COG. So I look and I can notice that it's variables 10 and 11, those being ADAS, COG, and meters walked, as well as variable 1, ID, and time 2, that I'm including, and then I'm going to keep this the same length of data as my data 2 data set, meaning that it's going to be 120 observations, but it's only going to include the variables of 1, 2, 10, and 11. Now, there's also another reason that I'm going to set up the data this way, and I'll get to that in just a moment here. So next, I'm going to set up a separate data set that's just going to be subsetted to include only the data from that are not time varying, meaning that I'm taking all my data that are not time varying here. So that's all the other variables that I have, and I'm only going to take time point 1 for that. So those data are going to only be 40 observations, and those are going to include ID, time, group, age, sex, education, height, weight, and BMI, since I'm assuming those aren't going to vary across time. Okay, now what I'm going to do is I'm going to set up different data sets at each individual time point for the time varying variables. So I'm going to subset the data for that varying data set into time point 1 for varying dot 1, varying dot 2 again for time point 2, and then varying dot 3 for time point 3. So 3 different data sets, one for each time point: varying dot 1, varying dot 2, varying dot 3. Now what I'm going to do is I'm going to do another command here in just a moment, wherein I'm going to take the column names of varying dot 1, and I'm going to then paste those column names into my data set for varying dot 1 in a slightly different way, where I'm going to, instead of having the dot, or I'm going to add a dot to every single one of those data sets. So if you look before, there's now a dot 1 for each time point. So I have I'm going to have ADA's cog dot 1, meters walk dot 1, and so on and so forth. Whereas before there was no dot representing each time point. And that's going to be beneficial for us when I'm trying to develop both my longitudinal data set as well as my my data set that is going to be for my ANCOVA analysis. So both for mixed linear modeling and for ANCOVA, it's important that we follow this same sort of setup. So I now have a dot 1 for all my variables at time point 1, a dot 2 for all my time varying variables at time point 2, and a dot 3 for all my time varying variables at time point 3. Okay, so now what I'm doing is, as you can see here, I have I'm now going to use the DPLYR package. And what this is going to allow me to do is it's going to allow me to join all my different varying data frames together into a single data frame. And this is going to allow me to run create that long or that wide data frame that I want. So I'm labeling these data as wide.data, and then I'm going to first join the baseline data with the varying.1 data, wherein I'm going to do this by using ID joining it with ID.1 for the varying.1 data. I then use that percent greater than percent command, which is going to basically say, like, okay, hey, don't just remember that there's more stuff coming, that I've got other things going on here within this command. And so then I'm going to left join again the baseline or that little data set that I had there. So the left join data already with varying.2, and this time I'm going to join it by ID.2. So again, everything's being joined together into one data frame, just as you can see here. So I'll go ahead and I'll finish up that command, and then that's going to be our wide data set. So we'll have everything set up to run our ANOVA and ANCOVA analyses, and there's only going to be a few small things that we have to do in order to make our analyses run for our mixed linear model. So we basically have our data set up for ANCOVA, but now after that we only have to do one other command in order to get our data set up for a mixed linear model. So everything's pretty much all set up and good to go at this point. Okay, so let's go ahead and let's do a few more things just to get rid of some of the junk that's in that data set. If you notice, there was time.1, time.2, time.3. So I'd like to get rid of those variables just because it's kind of ugly in my data frame. So I'm going to get rid of them for right now. It will also help for when I'm setting up my my mixed linear model as well. So I'm using this grep command to say, okay, whenever you see time, I want you to go ahead and make a list of it. So I'm creating this function for each of my time variables, and it's being set up in this this sample data frame. So I just want to have one variable for time, if anything at all. So we're going to remove those in just a moment here. And to do that, I'm just going to go ahead. I'm going to again call wide data. And this time, what I'm going to do is this is going to help make it clear that I don't want to include at least in this instance, I don't want to include anything that is time vars or time within my data frame. So I'm going to get rid of those here in just a moment. And if you look at my data frame again, as you'll notice here, there's no longer time variables associated with this. So no longer time, time.1, time.2, time.3. So it makes it a little bit cleaner. It's not the only way to do it, but it's a little bit faster, in my opinion, to run just two lines to run these lines of code rather than go searching through your data for anything that's like time related. So you're probably going to have a larger data set when you do an RCT, so there's no point searching through your data set to try and find individual variables. And then lastly, what we're going to do as well is I would like to just get rid of a few or change a few of the names of variables. I want to get rid of underscores, and I also would like to get rid of the dots in my data set as well. So we're going to use this gsub command, which is going to allow me to get rid of first the underscores, and then I'm going to use the gsub command again to get rid of the dots within each of my time varying variables as well. And here I'm just going to be changing it from dot one to baseline. So slight changes. It will make it easier for me in a moment here when I'm doing my mixed linear model, and I want to make sure that you all understand that that's going to be something that's going to be beneficial for us. Okay, so now what I'm going to do is I'm just going to set up this other new data frame called baseline. The reason I'm going to do this is just because I like to have one that's set up just using my baseline data for every single variable of interest and not just my variables that are not time varying. And the reason I'm going to do this is because it's important to still look at our baseline data and look at baseline outcomes for each group, and to summarize our data for like a table one sort of data summary. So here, what I'm going to do is I'm just going to develop a basic data summary for the variables that I think are going to be of interest for my RCT, and those would be age, sex, education, BMI, ADAS cog score, and then also meters walked. And so from here, now I'm going to use the table one package in order to develop a table that I can then use to summarize my data. Now it's important to note that table one does give p-values for group differences, which is a little bit annoying because I don't want to include those. I would just ignore those when you're using this package, just so you can get an idea of what what the groups look like at baseline. But we don't care about what group differences are significant. So again, even if you're using this package, do not look at what the group differences are. Don't worry about what those group differences are. Those group differences can be due completely and totally to chance, and it's not something that we should concern ourselves with in terms of the analysis itself. So we're going to, again, just set up this table one so we can look at what our groups look like at baseline in terms of sample characteristics. And from there, then we'll get into the analysis of covariance. And so we can see that there is a significant difference between groups in terms of the in terms of meters walked. But again, that doesn't matter because that is due completely and totally to chance. So don't worry about what those group differences are at baseline because it doesn't matter. It is due to chance. Baseline descriptives, we're going to go ahead and we're going to run our basic ANCOVA model. We're going to need to set up our model. And so just as a reminder, the way that we set up our ANCOVA model is that our model is going to be the final outcome of interest. So in this case, for right now, we're just going to focus on the meters walk test. So again, our outcome of interest is going to be meters walked at final, and that's going to be our dependent variable, and then our independent variable is going to be group. So again, we will use the command of lm. We're going to set up that model with meters walked at final, so meters walked. Always need to control for in our ANCOVA model since we need to control for. See, there is no effect of group on our model of looking do some additional covariates within that model. So right now, this is just our basic summary model, but we might think that some things may account for differences that exist between groups. And so one of those may be things like age. Assume that people that are older probably walk a little, probably can't cover as much distance minutes. And biological sex, of course, is something where we would assume that females don't have as high cardiovascular fitness as males, so we may want to include those two things as covariates. So run, relatively speaking, the same model. Again, looking at meters walked at time point 3, variable group as our major independent variable of interest, and then our covariates are going to be baseline meters walked, age, same model, and let's see what the result effect of accounting for each of our covariates. Away is that it's going to be difficult for us to be able to determine right away what are the differences between groups. So do is rather than using the summary, and we can use ANCOVA, and that will give us our basic ANCOVA table. That the p-values for these are slightly different from the p-values for the summary table. And for why that is in a minute, but I promise that these p-values, in fact, are the same for comparing between group differences. So the ANCOVA command to be able to look at between group differences, and we are focused on looking at a between group contrast in particular. So we would do that is we're going to use the ls means command. So as you probably remember from before, we're going to use a ls means command in order to be able to identify our differences are between groups. Just go ahead and we will type in ls means here in just a moment, and then we'll go ahead and we'll look at model number, and we're just going to use the first one, just our basic model, and we're just going to look at the ls means per group. And as we can see here, that the intervention group got about 344 meters walked in 6 minutes versus the control group, which was getting about 342 meters walked after accounting for baseline differences. Us right away whether which group actually had more, or whether there was a between group difference. And so in order to do that, we can use a contrast statement, just like we've done before, where we're going to enter that ls means command, same information as before. We're going to, on top of that, control. Adjust for our adjust for nothing. So again, we can do some adjustments, and those can be things like 2 key or something like that, but we don't need to do that. And if we look at the between group differences, we can see that there was about a 2 meter difference between groups, which is really not much. And as you can see here, if we look at the p-value for these between group differences, it is roughly going to be the same as our summary, as what we got in terms of the p-value for the summary statistic. So When we run the summary command, that's what's going to give us, at least for the ANOVA, or for our ANCOVA, it's going to give us the same as the between group differences that we're looking at from our contrast statement. We may want to have the 95% confidence intervals on top of having the p-value and the estimated between group differences. And to do that, we can just enter in the following code in order to be able to get the confidence interval. We're just going to wrap our contrast statement in confint, which is going to give us our contrast, our 95% confidence interval. We're going to put param because that's going to indicate that we want a parametric confidence interval with a level confidence, or 0.95 confidence, and then we can see the upper and lower bounds for our confidence interval. And as you'll probably notice, the confidence interval is pretty much 100% surrounding zero. So there's not really, it's pretty much in either direction. So as little as 104 meter difference favoring the control, and as high as 109 meter difference favoring the intervention group. So as we can see here, there's definitely there isn't much sign that there were differences between groups in terms of the problem with these data that you probably might have been thinking about is, do we have complete data for everybody? And the answer is no, and I'll show you right now. So if we look at midpoint, yeah, we do have complete data at time point 2 with 20 individuals in the intervention group and 20 in the control. But when I change that to time point 3, I noticed that I only have 34 individuals total, or intervention, 3 from the control. And so when I'm running a ANCOVA as of right now with these data, I'm actually only using a complete case analysis. I'm not using all participants. And so thus we need to impute data in order to be able to have a complete intention to treat analysis. And so one way of doing this is going to be to run a observation carried forward, and the other one is going to be to run a baseline carried forward. So we're going to set up a new data set called ydata2, and this is going to be using the Diffler package again, and we're going to use the mutate command in order to create new variables wherein we're going to account for any missing data. So to do this, this is going to be using this mutate command. We're going to create a new variable first called meters walked LOCF, or last observation carried forward at time point 3. And in this instance, if we're going to use the if-else statement, so in the event that data is NA at time point 3, then, or meters walked dot 3, then we are going to use the data for this individual at time point 2, since we know everybody has complete data at time point 2. And if they do not have missing data at time point 3, meaning that their data is complete at time point 3, then we're just going to use their data at time point 3 instead. So there's no reason to thing for baseline carried forward. So in this instance, we're just going to carry that individual's information over from baseline and in particular. And so I'll show you that in just a second here. So it's basically the same principle. We'll create called meters walked BCF.3 using the if-else statement. We'll then specify that in the event that the data is missing at time point 3 or is NA, then we're going to use the meter. If their data is complete at time point 3, then we're just going to go ahead and we're going to use their data at time point 1. we'll rerun. Our first, let's just look at the effect model. We can see that there seems to be a little bit more of effect, but it's still not significant. And same thing as well for baseline carried forward. So oftentimes this using this type of imputation is um, for baseline carried forward is quite conservative. But in either way, this is probably not the best way to impute missing data unless we have to. I'm not going to go over thing that we would also consider to make something like a multiple imputation for with multiple is we're going to reshape our data for our linear mix model. And the first thing that we have to do is we have to change our data set from that wide format back into a long format. So what we're going to do wide.data, and we're going to just reshape that a little bit in order to make it into a long format. So there's going to be ID, but original format, that would be the long format, but we have time one, time two, and time three. This new format we're going to have is only going to have time two and time three, and it's also going to have, we're going to have the baseline variables accounted for separately. So this is going to be something that we can use for our RCT analysis. And you'll notice that there are slight subtle differences, but it's important. Take that ID variable, and we're going to shape this data by ID based on the data that are time varying. So those are columns 11 through 14. All are time varying variables of ADAS-COG, time points 2 and 3, and then meters walked at time points 2 and 3. This will be able we also need to put in the direction. So in this case, it will be long format rather than wide format. And the separator is going to be something that we would use for each time point. So in this case, that there's going to that variable. So you need to be very careful about having dots in your data set for doing once we run this command, it's shorter. It's only going to contain 80 variables or 80 observations instead of 120 because we looking only at time points 2 and 3 for our our variables of interest, those being cognition or meters walked. So just be careful with how you set up the data, but this is going to make a lot more sense in a second about why we set up these data this way. Set up, we're going to go ahead and we're going to get into our linear mixed model. So what we need to do is we need to check if even we can run a linear mixed model. And the best way to do that is to run a null model first. So since we're going to be using a random effects model. And so for this, we're going to use the Elmer package, and we're going to just have our dependent variable, again, meters walked, random effect of 1 over ID, which is our random intercept. This is going to help tell us whether there's enough variation in the data over time to make a random effects model worth our time. And I'll explain how that's going to look in terms of set up our null model. We'll go ahead, we'll put in the data, or which we're going to run that, and then let's take a look at the summary. Make a lot of sense, probably, but the thing that we're interested in here is in that random effects tab. We're interested specifically at the residual and ID variance. What we want proportion of the ID variance to make it worth our while to run a random effects model is the ID variance a large enough proportion of the residual variance such that we can run a random effects model. In this case, that would be 3855 divided by 16775. Whether there is indeed a significant. That means that about 23% of the variance in the forward with a random effects term. So that's a good sign. That means that we have a decent amount of variance that can be explained with a random effects term. And that's something that we should consider when doing this model. And that's why it will help to include this random intercept term. Okay, so next up, let's just go ahead and we're going to make our model. But first, let's go through what it would look like to if we were to run the null model with the random slopes model. So what you're going to see here is we're going to, again, use that meters walked as our dependent variable. And now we're going to include time divided by ID, or time given ID. This will give us a random slope, but obviously in this instance it's not going to work, and the reason it's not going to work is because if we use this random slopes command, there are not enough time points in the data. So you can see that there's an error given the number of observations and the number of random effects. For the term, the random effects parameters and the residual variance are unidentifiable, so the model is not converging. Now we can get a random slopes command to work using a different package if we want, but typically speaking, in most instances, we typically don't do that for an RCT. We typically only use random intercepts, but you can sometimes use a random slope if that's your area of interest. I would just suggest having a larger number of follow-up time points personally. Now let's go ahead and let's run our primary model. In order to do that, we're going to go ahead, we're going to use Elmer, and then we're going to go ahead and set up our model, wherein we're going to look at meters walked, given group by the factor of time. Again, this is the factor of time is done in order to, or treating time as a factor is done in order to create time as a fixed categorical variable. So we're doing that again in order to make time a fixed categorical variable. From here, we're then going to include meters walked at baseline, age, and sex as our covariates, and again, we're going to use or include that random intercept. So again, once we've done this, we're going to go ahead and we are going to go ahead and set up the model, and let's go ahead and let's run it, and let's see what it looks like. Okay, so you can see like this doesn't really make a whole lot of sense, obviously, if we're going to be using this as our primary outcome or as our output. But What we are going to do in order to make sense of these data for an RCT is, rather than using the summary effect, we're instead going to go straight in and we're going to look at the LS means. And the reason we're going to do this is because we're interested in trying to understand what are the between group differences at each follow-up time point. So we have two follow-up time points of time point 2 and then time point 3. In order to do this, we're going to use the ls means command, but this time we're going to go group by time. And from here we can see what the difference or the different groups have for meters walked at each time point. Okay, so now that we've gone ahead and we've run our ls means command, let's go ahead and let's run a contrast statement. This way we'll be able to actually tell what the differences are between groups in terms of the effects of the intervention at each time point. So right now we're just looking at the estimates for each group in terms of what their means are for meters walked, but now we're going to look at the treatment versus the control in terms of the group by time effect. So now we're going to be able to tell whether there is indeed a significant difference between groups at each time point. So here we can tell that there's about a 37 meter difference between group at time point 2 and about a 38 or 39 meter difference at time point 3. But in both instances, there's not a significant difference between groups. We can also go ahead and we can look at a confidence interval to be able to determine whether there are what the confidence interval is for the between group differences, and this is probably something that you're going to want to include within your table at some point as well. And so this will provide us with all the information that we're going to need. And so you're just going to set up just like we did before for the ANCOVA model, this time just using the group given time as our LS mean of interest. And again, we'll set up just as before, wherein we're going to include that parameter command. And then we're also going to include our level, which is going to be the confidence interval of 95%. And as you can see there was just a typo, but again, we can see what the confidence intervals are, and both of them seem to be favoring the intervention group as compared to the control. However, in both instances, as makes sense given the p-values, there's not a significant difference between groups. So with that said, that's it for today in terms of the lecture that I have for you on how we would do an analysis of a randomized control trial. I'll go ahead and I would suggest going through the practice problems next, and then I hope you'll join me for a separate video on the answers to the practice problems that I have for you. Thanks again for coming.